Critical exponents are fundamental parameters that describe how physical quantities behave as a system approaches a second-order phase transition. For example, as a material nears its critical temperature, properties like magnetization, susceptibility, and specific heat change in predictable ways. These changes are characterized by critical exponents, which are measured in experiments and often differ from theoretical predictions, such as those from mean field theory. Despite these differences, critical exponents provide a universal language for understanding phase transitions across various materials. In this scene, we'll introduce the concept and set the stage for exploring their significance in physics. When scientists measure critical exponents in real-world materials, they often find values that differ from those predicted by mean field theory. For instance, in three-dimensional systems, the order parameter exponent beta is about 1,3, susceptibility exponent gamma is roughly 4,3, correlation length exponent nu is close to 2,3, and specific heat exponent alpha is approximately 0. These values are remarkably consistent across different materials with the same spatial dimension, highlighting a surprising uniformity. This scene explores why these discrepancies exist and how experimental results reveal deeper truths about the nature of phase transitions. The concept of universality is a cornerstone in the study of critical phenomena. It suggests that many different physical systems behave identically near their critical points, regardless of their microscopic details. These systems are grouped into universality classes, which are determined by factors such as spatial dimension, symmetry of the order parameter, and the range of interactions. For example, both the liquid-gas transition and the ferromagnetic transition in uniaxial magnets belong to the same universality class because they share up-down symmetry. This scene explains how universality classes simplify our understanding of complex systems. Universality classes are determined by three main factors: the spatial dimension of the system, the symmetry of the order parameter, and the range of interactions, short range versus long range. Interestingly, the critical exponents do not depend on the specific details or strength of the interactions. This means that vastly different materials can exhibit the same critical behavior if these key factors match. In this scene, we'll break down each factor and show how they influence the classification of systems into universality classes. To illustrate universality, consider the liquid-gas transition and the ferromagnetic transition in uniaxial magnets. Both belong to the same universality class because their order parameters share up-down symmetry, represented by n equals 1 in the Ising model. This symmetry leads to identical critical exponents, despite the systems being physically different. Such examples highlight the power of universality in predicting behavior across diverse materials and underline the importance of symmetry in classifying phase transitions. The table of critical exponents provides a clear overview of how different physical properties behave near the critical point. The main exponents include alpha for specific heat, beta for the order parameter, gamma for susceptibility, nu for correlation length, and eta for the correlation function. Each exponent has a mathematical definition, such as C T alpha for specific heat and chi T gamma for susceptibility. This scene presents the table and explains how these exponents are used to characterize phase transitions in various models, including mean field, self-avoiding walk-saw, Ising, XY, and Heisenberg. Different models yield distinct values for critical exponents. For example, mean field theory predicts alpha equals 0, beta equals 0, 5, gamma equals 1, nu equals 0, 5, and eta equals 0. But in the self-avoiding walk-saw, Ising, XY, and Heisenberg models, these values change, reflecting the influence of symmetry and dimensionality. The table shows how each model's exponents differ, offering insights into the universality classes they belong to. This scene compares these models and highlights the importance of choosing the right model for accurate predictions. Scaling properties near the critical temperature can be derived using the renormalization group. The spatial correlation function g, r, depends on the correlation length psi, which becomes the only relevant length scale near the transition. The homogeneity relation g, rt, equals g, r/b, tb1/nu, shows that the system appears the same at different scales if temperature and distance are adjusted properly. This scene explains how scaling and homogeneity unify our understanding of critical phenomena and reveal deep connections between physical quantities. One of the hallmarks of scaling theory is the mathematical relationship between critical exponents. For example, the divergence of susceptibility, cha, is linked to the correlation length xa by the equation gamma equals 2 eta nya. This relation demonstrates how different exponents are interconnected, allowing physicists to predict one exponent based on others. Understanding these mathematical links is crucial for grasping the full picture of critical phenomena and scaling theory. In this final scene, we summarize how these relationships tie together the concepts explored throughout the video.